Cool. Hey, good morning, everybody. My name is Primiano. I come from the London Google London team. I'm the TL of this memory infra team. Great pleasure to be here talking. So thank you for coming. So memory infra, we have like 30 minutes today. We have this team trying to build tools to understand and debug and hopefully solve memory problems in Chrome. So 30 minutes today, I'll talk about, first of all, about what are the problems that we're trying to solve, how we are dealing with this from the technical viewpoint, and then Petr is from the same team. Want to say hi?
Hi.
He's going to show you actually some live demo, and he's going to show the tools that we're building in action and tell what we are doing next. So first of all, problems. Everybody loves problems. Facts, first of all. As you might have realized, Chrome lately tends to use kinds of memory. And if you didn't realize that, definitely people outside realize that. And I just want to make it clear, it's not just a PR problem. Like, using a lot of memory means that we are bad citizens out there. It means that, especially on small devices, on smartphones, we cause other tabs to be evicted, or cause other apps to be evicted, and cause the general experience on the phone to be bad. So we need to do something to solve this problem. So what do we do to solve this problem? Well, we need data. We need to figure out and understand where and how Chrome uses memory. And here comes the tricky part, because as you might imagine, understanding the Chromium code base is not that simple. Understanding memory in the Chromium code base is not that simple. So this is something that happened very often. I had a discussion on Chromium Dev just a few days ago with somebody. It was like, okay, we want to understand memory in Chrome. Can we just instrument malloc like everybody does? And it's like, the answer is, you can do that, but that is not really the full story, because like in the browser process, yes, we do use malloc, use a lot of mallocs. The thing is that malloc itself has different implementation, so depending on the fact that we are on Android or Linux or Windows, we have different things backing malloc. But that is not the entire story. We have also shared memory, because we tend to have shared buffers between browser process and renderer process and GPU. And we have discardable memory, which is a completely different world. And then we get to the renderer process. And as you have seen from Haraken talk yesterday, we are like discardable and shared memory, and the content layer uses malloc, and Blink uses mostly partition alloc. But is switching to oilpan, and in the meantime, we have V8, which is does its own memory management. And then we have the GPU process, which has like a transfer buffer, command buffer, and you have the GL driver doing all sorts of shady things under our pegs, and the system UI doing something similar. So the situation is pretty complex, and we need to rationalize all of this in order to get a full understanding of what's going on in Chrome. And this is essentially the problem that we are tackling here. There is another problem, which is make all this thing working at scale. So people tend to think that the way we should solve this problem is by saying, okay, let's create a task force. We get some GPU expert, Blink expert, Chrome expert. They fight for a month or whatever it takes to bring memory usage down in Chrome, and we call it a day. The thing is that is not really the way we should work, because one of the things that people forget is that ours is a very extremely active code base. We have an average of 200 commits per day, which means that every day a lot of cool features come in, but every day at the same time, sometimes we tend to have regressions, and most of the times these are not really intended. They are just side effects that the original author didn't think about. So we have a lot of stuff happening every day, and we cannot just fight on a monthly or yearly basis. So this is what we did in the past. If you look at what we did in the past, the situation was pretty much like this. Like, Chrome memory goes day by day, increases until somebody is like, oh, damn it, like that is too much. We have to bring all these people and fight, and then it goes down. And 1 year later, back we are, and we need another task force to bring memory usage down. And that is, in my opinion, not the way we should work. That is not healthy and doesn't help. We cannot wait for problems to become gigantic before we solve them. So yeah, that is pretty much the situation. So one of the major problems has been that so far, every time we deal with memory, We have like a huge variety of tools which are very specialized or like are just for some platform, and very few people know how to use them, so very few people will do with this problem. They fight the fire, bring memory usage down, but then people move on, and all these tools get unmaintained, and nobody knows how to use them anymore. So the idea here is that instead we need some tools that scale with Chrome, which means that they just work out of the box, are part of the are part of Chrome, and they survive. It can be used by others when the fire is over. And the other important thing is that we need something to address the full performance lifecycle. It's not just a matter of fighting fires. We need something to keep track continuously of memory regression and avoid that they sneak in. So all the tooling that we are going to show is part of Chrome tracing. There have been quite some talks yesterday about Chrome tracing, so I have the feeling that everybody has an idea of what is Chrome tracing. So the idea is that these tools here should be used, first of all, to spot problems. Like, not everybody can have a full understanding of the Chromium code base. So what you really want to do is having a way to take a look to a trace and say, like, okay, this sounds like a problem that belongs to this team or this person. You want, first of all, a way to shard problems, to route problems to the right person. And the other thing is that once you are the right person, you want a way to reproduce the problem, you want a way to investigate and look into details, and you want a way to understand if you manage to fix the problem or not. So what are the use cases of all these tools? There are essentially three main use cases that we are dealing with here. One use case is you're a Chrome developer, so you are debugging something, you want to see what's going on, so you open Chrome tracing, you grab a trace, and you analyze the state of Chrome. And we have demos in the last part of this presentation to show what this actually means and how it looks like. The second problem is outreach. Sometimes we have a problem of this form of we have a web developer or a partner out there, and it comes to us, files a bug, and says like, oh, damn it, Chrome is using 12 gigs of memory. And until a few months ago, we had no idea we didn't know what to tell him because we had no idea to get debugging from him. And then you have to ask him like, yeah, you have to do all these magic steps to get some debugging information, but that is usually hard. And what we can do today, we can ask him like, hey, can you just grab a trace? Can you open Chrome tracing and grab a trace? So the person opens Chrome tracing, sends us the file, attach the file to the bug. We can open the file from the bug, and this is true story. We open the trace, and it's like, David, you have 42 extensions. Like, what do you expect? Like, third use case, this is very interesting. We have a continuous integration waterfall. We have a performance waterfall. So this is something that we are building in this quarter. So the idea is that we use the same technology that is used by developers, and making sure that when we run performance tests, we attach the full trace to the dashboard. And when we get a performance alert, you can download the trace from the dashboard and say like, okay, the performance alert told me that something was wrong. I want to take a look to what was that something. You want to look to details. So you can get the trace, load into tracing, and see what was the cause of that alert. So this is essentially the background, what we are doing. Now the interesting question is, how does all this thing work technically before we get to the demo? So this is a way to get some insight about what's happening inside of Chrome. So you might be familiar with the overall idea of tracing. The idea of tracing is that the code base is instrumented with trace events like this. So all over the code base there are this trace event. We are initializing some widget, or something is happening in the media stack, or something is happening inside of Blink. So all these trace events end up in a log instead of tracing, and when the tracing is over, this log is serialized into a tracing file, which looks pretty much like this. So far, all of this is about runtime profiling. So you see when something starts, when something ends. There are a lot of other things that tracing can do these days. I don't know if you're familiar with frame viewer or async slices or following the IPC. So the idea here is that we are adding another dimension to tracing, which is memory. So making memory a part of this tool, which is used to debug essentially everything in Chrome. So what is the idea here? The idea here is that somewhere in the code base, we have this thing called memory dump manager. The idea is that at periodic intervals, we collect snapshot of the state of memory. So what does it mean, the state of memory? It means mainly two things. So the idea is two things. Like one thing is system stats, like the thing that you're used to see in the task manager, the thing that probably the way you did debugged or diagnosed memory issues so far in the various platforms. But the other idea is that usually these things are not enough, because they don't tell, they don't give enough detail to understand what's going on inside of Chrome. So inside of Chrome, we have all these probes, what is called these blue rectangles, which are called dump providers. So the idea is that the code is being instrumented, and each team or sub-team took care of getting, like, putting some instrumentation, which essentially really means just extending an interface, and when you get a callback, you provide everything you know about your subsystem. And all these dump providers dump inside the trace a snapshot of their state. So we have something for V8, something that dumps the statistic of partition alloc, something that dumps the statistic of the compositor, and they all end up in this snapshot. And the snapshot ends up inside of the trace. So when we open the trace, and Petr is going to show that later, you see that now we have all this information that you can analyze and inspect on the timeline. So that is the overall idea. What is the current status? We targeted supporting all the major Chrome platforms, which means that if you get a Canary today, all the stuff that we are going to show works in Linux, Android, Windows, macOS, Chrome OS. What do we have today, which essentially means what did we instrument so far? We have general statistics about coming from the system, statistic from malloc, statistic from partition malloc. We have a lot of details about partition malloc. We are going to see them later. Statistic about oil pan, isolates and heaps, isolate heaps of V8, discardable memory, SKIA caches, web cache, compositor, GPU buffer. As a general invitation, like if you ever own or just know about a subsystem of Chrome, which is something like a cache or something which holds some memory or keeps track of something, keep in touch. Would be very, very useful to have this information exposed in Chrome, because it means that people can understand what's going on. You can get more feedback to understand if your component or your subsystem causes a memory problem, in a memory bloat in Chrome. And what happened in the past is that most of the time when we asked these teams to instrument their stuff, is that the day after they do the instrumentation, they look at the trace and they're like, oh, we didn't realize that we keep all of this stuff. We can actually drop it. This happened when we did partition. We got the statistic about partition alloc, and this happened with the GPU folks when they did instrumentation of the GPU buffer. So really, that is a very good first step to have understanding from your own viewpoint about what your subsystem is doing inside of Chrome. Just quick description about what happens when you trace. So the idea is that, so Chrome is a multi-process application. So the idea is that if you want to have a good view of Chrome, you need a view of all the processes inside of Chrome. So what happens in reality is that we have at these periodic intervals that you can customize. You have IPC requests going all over the processes, so the browser acts as a coordinator, and each process essentially is required to dump a snapshot of all the subsystems that it owns. They all create these snapshots. The snapshots get, like, the confirmation gets back, and all these snapshots end up in the trace. And then the UI is able to recombine all these snapshots coming from different processes and aggregate all this data. I think I'm gonna skip this. Threads are bad, don't use threads. So what is the content? So once you get all this data here, how does the snapshot look like in the trace? So the main idea is that all these subsystems that I briefly talked about report a tree with some information. So let's just make a short example. Say that we have a dump provider that can tell all the statistic about partition alloc, and the dump provider can tell all the statistic about caches in SKIA. So what you will see very soon is that they provide data of this kind of form. is a very simplified view, but gives an idea. Is okay, partition alloc says, I know about, like, these are my partitions, like buffer, layout, node, and Skia says, like, oh, I actually have a couple of caches. I have like caches for glyphs and caches for resources. And they provide, in each snapshot, their status is, okay, the buffered partition is 5 megabytes, contains 5 megabytes of stuff, layout 3 megabytes, 2, et cetera, et cetera, et cetera. And the UI knows how to add it up and says, okay, this is the total for partition alloc, this is the total for Skia. So far, so good, no rocket science. So where is the tricky part? The tricky part is that, as you can imagine, sometimes these subsystems are not disjoint set. They are interact with each other. So let's make another example. This is a real one. There is also web cache, and we have a dump provider for web cache which can tell the status. And web cache has some cache scripts and some cached images. But now the problem is that these these scripts that are cached and these images, they are not isolated. Like, actually what happens in reality is that the scripts have been allocated, like take some memory that has been allocated via partition alloc, and the images have some, uses some resource cache that lives inside of Skia. So one of the things that, the very nice thing that all this tool does is having a way to keep track of this relationship. And you will see in the demos that there is something which is called inside the trace the effective sites, which essentially is a way to keep track of this relationship and make sure that we can still we can express the relationship between the various subsystems that we have, and we can keep track in a way that makes sense at the total level about this number. So it's a way to create a responsibility map. You can say, this is my status from the partition alloc viewpoint, but at the same time, there is something else which is owning and is responsible for this memory. And there is a way to see all this graph and show all these relationships. So at this point, I think that all the boring part is done. You can go
and the exciting stuff is here.
Exciting.
Okay, so hi, I'm Peter, and I'm going to show you how all of this that Primiano has talked about translates to the tools that you can use. So how can you grab memory trace? So there are essentially 3 ways to do this. The first one and the easiest one is through the UI by going to Chrome tracing, which has been discussed yesterday and will definitely be discussed more today. The second option is to use the command line, which allows you to do startup tracing, and I'm going to briefly discuss that towards the end. And then also what's coming soon is the ability to get memory data from the bots in telemetry benchmarks and then have automatic alerts. And so I'm going to show you how to use the UI because that's the simplest and most straightforward way to do this. So let's hope that it works. So how do you do that? So this is Chrome Canary. There was no need to recompile anything. You can use this right now if you just install Canary. And what you do is you go to Chrome tracing. Okay.
Oh, that's my layout.
It's fine. Okay. You go to Chrome tracing. You click record, and then here you enable memory infra. And then you click the record button here, and you start recording, and then you can do whatever all the crazy stuff in Chrome. And then once you're happy, you stop the recording. I'm not going to do that right now because it takes some time to save the trace and import it, but trust me, it works. And then what you get in the end, once it's loaded, is you get this. So this is Trace Viewer, and let me maximize this. Okay, this is Trace Viewer, and you get this kind of timeline view from the left to the right. And the important thing here is that at the top, you have these blue and pink dots, and they have M in the middle, and that suggests that those are memory dumps. So at each of these points where there's a dot, the memory was dumped from all processes in Chrome. The dark blue dots, those represent light dumps, and the pink dots, it's not as visible here, but hopefully you can see it. The pink ones, so for example, here is a pink one. Those represent heavy dumps. The difference is that in the light, so in all of them, all subsystems dump their information, but in the detailed ones, there's more data. And the reason why we can't dump everything at the same time each time is that the trace would become too large and the runtime would be impacted too heavily. The default rates here are that we do a light dump every 250 milliseconds and a heavy dump every 2 seconds, but that can be configured, so you can change that if you want to. Okay. So in addition to these dots, you also get two charts here. First one, the stacked bar, that shows you how memory usage has evolved over time per process. And we also get memory per component. That's the light chart here at the bottom. So this already gives you quite a nice idea of how much memory is used where. But you can dig down deeper and say select a particular memory dump. So let's select one of the heavy dumps. And what you get here is the analysis view at the bottom. And this is where things start to get interesting, because you can find out much more information about memory usage at the particular time point. So you get this overview table with processes as rows, so you can see how many processes there are. If there are 40 processes with extensions, well, then your problem is solved. You know what the issue is. And then per process, you get these columns that represent the system stats. So those are the blue columns. Those are numbers that you probably have already seen before in other tools, such as proportional, set size, private dirty, etc. And also, the really interesting and important part here that separates us from the other tools are the Chrome internals. So those black columns here that represent things like Blink, V8, etc., and their effective sizes. But that's still not. You can still get even more information. So for example, let's say that we are interested in the size of V8 on the verge. This is the last process here. So you can click here, and you get component details. So you get even more details about V8. And you can see you have per isolate information, and in each isolate you get per heap space information. And these are really, the thing to take away here is that in addition to the effective size and size that you get for everything, you get allocator domain-specific knowledge. So for example, you get allocated object size and virtual size, which is specific to V8. Blink gives you different types of information specific to V8, to oil pan, etc., etc. So this really gives you a very detailed knowledge of what's taking up how much memory. And as Primiano mentioned, there's this notion of size and effective size. I'd just like to point out that here they are equal because V8 is the kind of end user of memory. There's no one else in Chrome that allocates from V8, but this does not apply to everything. So for example, if we look at the discardable memory, which other components are using, you can see that here suddenly the effective size is not equal to the size. The effective size is smaller. And the reason for this is that other components have allocated from it. So for example, here you can see that web cache has allocated memory from the discardable memory, and you can see here the size of that allocation, and the effective size here is 0, because the idea is that discardable memory should not be kind of charged for this memory, because it's web cache that uses it. And here, this is the UI shows you exactly what part of Chrome was using this, and you can then navigate through the analysis view to see that. So yeah, so this is just to demonstrate that the usefulness of the effective size. Okay, but sometimes this is good for many components, but sometimes these component details are not enough. That's the case with allocators, because if you're a Blink developer and you want to know what's using memory, the statistics that partition alloc will give you here, the kind of allocated objects, are not enough, because this is good for partition alloc developers, but not for users of partition alloc. And so what we have done is get even more. We were able to get even more detailed information by instrumenting heap allocations of partition alloc. And so that's what you get here at the bottom. So in addition to that breakdown of the component, you can also see which parts of Chrome, which you get pseudo stack traces of all allocations, and these are aggregated, and you can navigate them in a top-down view, and you can see where exactly in code how much memory was allocated from partition alloc. And we provide both a top-down view as well as a bottom-up view, so it's really, you can get very detailed information that's very actionable. So this is it. In addition, as we said, we have the system stats. So you can also, for example, get we provide you with all memory maps here, and they're classified by their type. So you can, again, if this is what you're interested in, this is also included in the tool. So we give you as much information as is possible, but we classify it and show it in a Yeah. Okay. Hierarchical view that's easy to use. And now so this is all really great, but what we think separates us from other tools is that not only you can look at a particular single snapshot and see how much memory is used in it, but you can also compare two snapshots and see how memory changed between those two snapshots. So if I also select this dump here, suddenly we get the diff between the two timestamps. And now here you can really easily see where memory has increased or where it has decreased. So if there's suddenly a spike, you can really see which component caused that spike. And this is not only, you don't only get this in the overview table, but you get this in everything, including the heap dump. So if you now open the heap dumps at the bottom, we'll see exactly in which functions more memory was allocated. And we think that this is very, very actionable for people to figure out where more memory is being used. So this is what the UI offers, and we hope that you will like it, and feel free to grab us and ask us questions or have more suggestions. So this is how you do it through the UI. Let me skip this. The demo worked, so we don't need these. So that was the UI. Another way to do this is to do startup tracing. The benefit here is that you can get memory data from the very beginning of Chrome, or also from the very end of Chrome before it's closed. And to do that, all you have to do is create a JSON file that specifies these intervals for the light dumps and heavy dumps, and then just start Chrome with a flag that starts the tracing. And again, in the end, you get the same trace that I showed you when you did Chrome tracing. So it's easy to use, and there's more information in the wiki. Okay. And then the final thing that we said is what is coming now are telemetry benchmarks using memory infra. So what's the value here? So until today, we already did have some memory benchmarks, but we mostly tracked totals from the system. And this has two issues. It's firstly that they're quite noisy, and secondly, they're not very actionable, because if you suddenly see a spike in total memory usage, you have no idea where to look in Chrome and what to look for. So what we do now is we keep track of individual components, and this gives us two benefits. Firstly, most of them are much less noisy, sometimes even on the order of hundreds. And also, they're much more actionable, because you will see which component of Chrome increased, and then you can open the associated trace and dig down through the UI, as I've just shown, and see what really happened behind the scenes. Also, when you run benchmarks from telemetry, you get, no, this is not what I want. You can also get the results that you get from telemetry running benchmarks include all the stuff that I've discussed, so you get this detailed information for individual allocators, etc. So you can also run this from that framework. Okay, right. And so that's how you can get the data from, or how you will shortly be able to get the data from telemetry. And so what's the plan now and for the future? So in telemetry, we want to switch all existing benchmarks to use memory infra for the reason that I just described. So it's to reduce noise and to improve actionability. And that is currently being beta tested already. Also, we want to be able to use that data and get fine-grained alerts. So if someone lands a patch that suddenly increases the usage of memory, we want to get an alert immediately, so that the perf sheriffs can react to that. And also, we want to simplify the performance dashboard UI so that people could use this easily. What I mean by simplify, if you look at this, it's very complicated to find the data on the performance dashboard at the moment. So that's what we want to improve, because there's too many categories, and you really have to know what to do. And then we also would want to integrate with perf insights that were mentioned by Nat yesterday. So we want to be able to get data from the field from our end users using deep reports, and integrate the numbers that we have with the performance insight mappers, possibly included in the Rail++ score that was mentioned yesterday. And that's all. So thank you very much for your attention. And if you have any questions, feel free to ask us. Thanks.
Sure.
Will all the dumped recorded data be held in the memory, or it can be dumped to the disk from time to time?
That was an interesting question. So the current design of tracing allow to save to the disk the trace only at the end. What you can do, so depends what is the use case that you want to, what you are aiming to, aiming at. What you can do is, if you want to record a long trace, you can set the interval to be very, very large. You can say get one snapshot every 30 seconds. So the file gets written at the end, but you can ask to make the dumps like very infrequently, so you are sure that that will fit in the disk and will not explode the trace size.
Yeah, I ask this question as we tried this tracing on some devices, especially for the low RAM devices. It even get our browser, get the Chrome killed by the system.
I say, yeah, that's an actual problem. We have brainstorming sessions today. We're trying to figure out one of the answer there is that we are not making a smart use of memory for the trace itself, which is a bit bad. But we're trying to figure out a way to be more efficient there. I don't know if the answer is going to be offloading to disk or just being smart and in the way we store the trace log. So we have. I know that is a problem. We are trying to figure out.
You.
Super cool tool. Thanks for doing that. Well, I'm especially interested about the diff feature. Do you sync the memory events up with the V8 garbage collection? Because after V8 garbage collection, memory will significantly decrease, right? We will free up memory. Oilpen will free up memory. Partition alloc might free up memory. The thing is, as long as we don't do a full garbage collection in V8, memory will continuously increase. This is how garbage collection works. So I'm wondering, do you sync up at one point? Or maybe V8 full garbage collection would be a good point in time where you create one of these full.
Right. So we have a bug open precisely for V8. So the idea there is that, so right now DC Answer was doing the periodic dumps, 2 seconds, everybody's happy. The idea there is that the dumps, we can get hint from the code base and say like, hey, actually, now is a good time to get a dump because I did a garbage collection or there was a large scroll. So one of the next thing is being able to trigger the dumps from the code base instead of just having the periodic dumps. And I think that V8 is definitely going to be the first case for that.
So what's the current difference between the heavy and the lightweight dumps that you
mentioned?
It's
the amount of detail that you get. For instance, in partition alloc, light dumps just tells you the total for each partition. Heavy dumps tells you the distribution inside the buckets. Same thing with Skia. Skia in the total dumps. So the total is always the same. The number don't change. But Skia just says resource cache is 1 megabyte. In the heavy dump says the actual fonts that contribute to the font cache. So this sort of trade-off between detail and the size of the trace.
Plus the detailed dumps contain things like memory maps, which are too heavy to be dumped all the time.